Hi all, it's a pleasure to take part in the Eli conference, a great pleasure. I'm only sorry that it has to be virtual participation. I thought I'd give a survey talk about the work I've been doing for the last 15 years or so on a particular problem, which on a subject that arose from something that I learned from Eli a long time ago. So this is interpolation of data by smooth functions in Rn. Let's see. Okay, so the subject started with the Whitney extension theorem, which I learned from Eli in a wonderful course in 1967. It changed my life. I'm actually not going to state the Whitney extension theorem. I think many of you know it, but it's the logical foundation of the subject. Okay. I'm not going to talk a whole lot about who did what. I'd like to get to the ideas. And so let me just record here names of people who made major contributions. There they are on the slide. Okay, let's get started. So definitions, well, we're going to interpolate functions within our favorite Banach space of continuous functions. Let's call that X. And so X for us is going to be Cm of Rn, the space of functions with m bounded continuous derivatives on Rn, or Cm alpha, the space of Cm functions whose mth derivatives are alpha, or a Sobel of space, Wmp, the function and its derivatives up to order m belong to Lp. So those are the spaces we're going to work in. Okay. A convention throughout the talk is that when a constant is denoted by some version of the letter C, that means it's a constant depending only on the choice of the space X we're working in and not on the particular problem we're solving in the context of that space. So for example, if X is a Sobel of space, Wmp of Rn, then these constants C, C prime, etc. will depend only on little m, p, and little n. Okay, so what's the problem? Well, suppose E is a finite set in Rn. X of E is going to denote the space of all functions, or let's say real valued functions on E, and the norm of a function in X of E is the inf of the norms of all the functions capital F in X that agree with little f on E. So we have a function little f on E, and we're trying to extend it to a function capital F in X. And this function should have the smallest possible norm. This inf in simple cases is already an inf, not a minimum, and that motivates the idea of an A optimal extension. So if you have little f, a function, and capital F an extension, and capital A a number, then capital F is an A optimal extension of little f if it agrees with little f on the set E, and its norm in X is within a factor of A of the inf. Okay. So given that notation, the problems roughly stated are this. Suppose you're given the space X and the set E and the function f. We first of all want to compute the order of magnitude of the norm of f to decide whether we can interpolate with a small norm or whether we need a big norm. And also we want to compute a C optimal extension of f, where C is one of our constants depending only on the space X. Now this is a vague statement of the problem, so I have to say what some of the words mean. So for example, to compute the order of magnitude of the norm means that we actually compute not the norm but some other number that I call the triple norm, with the property that the triple norm is comparable to the norm as shown on the slides. They differ at most by factors of these constants depending only on the space X. So we want to know roughly how big the norm of f is. Okay, what about computing a function? Well, a function is inherently an infinite object. What do we mean by compute? What do we mean by compute a function? Well, we're actually going to be thinking about algorithms to be implemented on a computer. I hope you don't think I've gone too soft. This is on the borderline with computer science or numerical analysis. And so what I mean by computing a function is this. We're going to enter the data, in this case little e, a big E and little f, into a computer. The computer then accepts the data and performs one-time work, and then it beeps to indicate that it's ready to accept queries. We can then type in queries and the machine will respond. The query consists simply of a point of Rn, and the response to a query consists of a function value and, let's say, all its derivatives up to order m, if our space happens to be Cm, so that it makes sense that such derivatives exist. So that's what it means to compute a function. Now, we want efficient algorithms that make minimal use of the computer resources. What does that mean? Well, for computation of a function, the relevant computer resources are the number of computer operations used in the one-time work. A computer operation is, let's say, add two numbers together or something like that. So the number of operations of one-time work, the number of operations to answer a query, and the size of the memory. Let's say one memory cell can hold a single real number. Let's say, for purposes of this talk, to perfect accuracy. Actually, there are more refined versions in which one worries about round-off errors, but for God's sake, let's not do that here. So there are three different things that we're trying to optimize. One would naturally expect trade-offs, but a pleasant surprise is that one can optimize all three of these things simultaneously. All right, now there are trivial lower bounds. If our set consists of capital N elements, then obviously the one-time work is at least capital N, because you'd better read the data. The query work is at least 1, because you'd better read the query and answer it. And the memory used is at least capital N, because you'd better remember the problem. In the other task, simply computing the order of magnitude of the single number, norm of f in x of e, the relevant computer resources are simply the number of computer operations for the calculation and the number of memory cells needed. Okay, and the trivial lower bounds there are similar, at least n operations so that you read the data, and at least n memory so you remember the data. Okay, now a significant feature of this problem is that we're interested in algorithms that always work for any finite set in Rn. So we don't assume, for example, that E looks anything like a lattice inside Rn. If we allowed ourselves favorable geometric assumptions on E, our problems would be several orders of magnitude easier. So just to give you the idea, I'd like to present a few delicate cases. So the first delicate case, in example 1, let's say our space of smooth functions is, let's say, functions with 5 derivatives on the plane, and capital E is the set of dots in the next slide. So here's our set of dots. Now notice that almost all of the dots lie very, very close to the x1 axis, and therefore, if we know the value of a function on these dots, we have excellent information on the function and its x1 derivatives, but we have a great lack of information on the x2 derivatives of the function. On the other hand, if we look at the point labeled x and some of its nearby neighbors like y, we can infer some information about that. And if the function capital F has a not so big norm in, let's say, C2, then that gives us information about the derivative in the x2 direction at the point z. The trouble is that x and y need not be among the 500 nearest neighbors of z in the set E, and therefore any algorithm that looks only at z and its 500 nearest neighbors is guaranteed to be seriously wrong. So we had better recognize this situation and respond to it quickly. In the second example, again our space is C5 of the plane, but E is a different set of dots, and here it is. In this set of dots, gamma is supposed to be an algebraic curve, the zero set of some low-degree polynomial in the plane. This is basically the same as example 1, except that instead of the x-axis, you have the curve gamma. Now, nobody tells you the curve gamma. Instead, our problem is to deal simply with the set of dots. And so if you're given that set of dots, you had better make yourself aware of the curve gamma and deal with its consequences real fast. Okay, and that's still not the worst of our problems. In example 3, x is C5 of R3, and E is the set of dots in the next slide. And in the next slide, our set of dots lies very, very close to an algebraic surface sigma and somewhat close to an algebraic curve gamma sitting on sigma. And so, again, we're not told sigma and gamma. We had better deduce that they're around from just looking at the dots and then respond. So there's a connection with real algebraic geometry. In order to solve the problem, one has to do some real algebraic geometry. Okay, so now let me explain what we're able to do. These are joint results with Boas-Klartag a long time ago. So, in this problem, our space X is Cm of Rn. E is a finite subset of Rn. This problem for infinite subsets has a completely different flavor that I hope to get to later in the talk. E has, let's say, capital N points. Capital N is finite. F is a real valued function on the set E. And so we're trying to compute a C-optimal interpolant, and we're trying to estimate its norm. And the result is that one can compute a C-optimal interpolant. Remember, C depends only on the choice of the space X and not on the particular problem being solved. The computation can be made using, at most, Cn log n operations of one-time work, C log n operations to answer a query, and n memory cells, Cn memory cells of RAM. That's the situation for the calculation of the interpolant. In terms of the calculation of the norm, you can compute the order of magnitude of the norm using at most Cn log n operations and at most Cn memory cells. Now, these upper bounds are within a factor log n of the trivial lower bounds that I just talked about. So they can't, for trivial reasons, these bounds can't be improved much. I believe strongly that these bounds are sharp, and I don't have time to explain why, and I certainly don't have a proof of optimality. But I think it's very likely. Okay. Now, how does one produce these algorithms? Well, non-trivial algorithms are often the result of mathematical theorems, and these algorithms are closely related to something that I'd like to call a refined finiteness theorem, and I'd like to pave the way for stating the refined finiteness theorem. Okay, so let's look at finiteness theorems first, never mind refined finiteness theorems for Cm of Rn. The first one was proved by the formerly Soviet, now Israeli mathematicians Brudny and Schwarzman. And their first theorem was for C2 of R2, and the theorem is as follows. Suppose that we have a big finite subset E in R2, and we have a function little f defined on that set. Suppose we want to extend it to a function in C2 of R2. Well, suppose we can do that for every subset capital S having at most 6 points in such a way that the norm of the extension is at most 1 for each 6-point subset. But perhaps different 6-point subsets give rise to different extensions. Nevertheless, that implies that the whole problem can be solved with C2 norm, let's say, at most 100. I haven't told you exactly which C2 norm I'm using, but all of the standard ones I picked 100 to be large enough that this theorem is true for any of the reasonable definitions. Okay, so if all little subsets of an interpolation problem can be solved, then the whole problem can be solved with only a slight degradation of the norm. More generally, instead of C2, one can do of the plane, one can do C2 of Rn or C1 alpha of Rn. There was, however, a barrier at C2. Spaces with smoothness more than C2 didn't yield to their methods. But they remarkably, in place of 6 points for n equals 2, they got the optimal number of points in dimension n. When n equals 2, 6 is optimal, as they proved. And they showed that for C2 or C1 alpha of Rn, the optimal number is 3 times 2 to the n minus 1. Okay. Well, that's a finiteness theorem. Let me explain what a refined finiteness theorem is. Again, this is contained in the work with Boas. So again, we fix little m and little n greater than or equal to 1. They specify the space of functions in which we're working, Cm of Rn. Then there are constants, C and K sharp, that depend only on little m and little n, such that the following holds. Okay, suppose we have a subset E with capital N points as usual. Notice I haven't yet told you that there's a function on E. There's just the set E. Then we can pick out a rather short list of little subsets. So our subsets are S1, S2 through SL of E. The number of subsets we pick is only linear in the number of points of E. That's the first bullet point. And furthermore, each of these S's is a very small subset, namely it's the number of elements is at most k sharp, just a constant depending on the function space for each L. So we have a relatively short list of little subsets, and now we bring in, once we fix those sets, we then bring in functions. And so for any function at all, if you want to know the norm in Cm of E, that is the inf of, how small you can make the norm of an interpolant with respect to Cm of Rn, then that's comparable to the max of the corresponding norms that you get by just examining each of the little subsets. All right, that has the effect that once you know the little subsets, you can calculate norms in linear time. Of course, you have to calculate the subsets, but they can be computed efficiently from E. I don't have time for the details. Okay. Let me give you a little glimmer of the proof. I said before, this is a survey talk. What I meant by that is I'm not actually proving anything. But let me give you a little glimmer of the proof of the refined finiteness theorem. And the story is that if you look inside the proof of the refined finiteness theorem, that's the starting point for the algorithms. The algorithms require additional ideas, but it's somehow based on the proof of the theorem. Okay, so to give the idea, I want to introduce a little more notation. And so Jx of f, J for jet, Jx of f is simply the nth degree polynomial, Taylor polynomial of f when expanded about x. And so that belongs to script p, the vector space of all Taylor polynomials, that is, of all real nth degree polynomials in Rn. So that's the little bit of extra notation. Now, okay, one has to ask the right question. The right question is the following. Suppose there is an interpolant. So suppose there exists a capital F in Cm with norm less than or equal to capital M, and it agrees with, capital F agrees with little f on E. Well, then what can you say about the function and its derivatives for a given point x? So what can you say about Jx of f for a given point x? And that question can be encapsulated nicely in this definition. So suppose we're given a problem, as usual by now, little f, capital E, and we're given a point, little x, which may or may not belong to E, and a number, capital M. Let's define gamma of xm to be the set of all jets at x of functions that agree with little f on E and belong to Cm. So, and not only belong to Cm, but their norms are less than or equal to the given number m. So this gamma encodes the previous key question, what can you say about the Taylor polynomial of an interpolant? It also, it clearly contains powerful information about interpolants. For example, you might ask, is there an interpolant of norm less than or equal to capital M, or have we been too greedy and made capital M too small? Well, if we've made capital M too small and there are no interpolants, gamma is empty. So the question of the norm, the best norm of the interpolant, is the question of deciding whether gamma is empty. And more generally, more sharply, we want to understand the approximate size and shape of gamma. Okay. Now, gamma encodes not only what I said before, but it actually encodes the real algebraic geometry of the problem. So the approximate size and shape of these convex sets gamma encodes the real algebraic geometry for the following reason. If the set E is close to the zero set of some low degree polynomial capital P, then the set gamma of xm will be very elongated in the direction P, P being a vector in script P. That's obvious if you disentangle the definitions, but I don't have time to disentangle the definitions. Okay. So to prove the refined finiteness theorem, we first understand the approximate size and shape of the gammas, and then we use that information to construct interpolants. That's the executive summary of the proof of the refined finiteness theorem, which in turn is the key ingredient for the algorithms. Let me give an application before I go to other problems. So the application has to do with removing outliers. So suppose we have a function defined on a finite set E. We're going to look for a small subset S contained in E, the outliers, with the property that if you remove the points of S from the problem, suddenly you can do a much better job of interpolating with a smaller norm. So here's a simple one-dimensional picture. This is the graph of a function. Well, we haven't drawn the function yet. There are dots. And the graph of the function is supposed to pass through the dots. 3 of the red dots can be regarded as outliers. And if only you remove them, you can obviously interpolate with a much smoother function than if the red dots were present. I have in mind in all of this that this should be useful for, let's say, trying to fit a smooth curve to experimental data. And maybe for 3 days, Charlie was operating the equipment and it malfunctioned. Okay, so the theorem on outliers is that the set E can be enumerated as a sequence x1, x2, etc. through xn in such a way that for any number k less than or equal to n, the set Sk, consisting only of the first k elements in the enumeration, the set Sk has the property that it's essentially optimal as a set of outliers, namely, given any competing set S with substantially fewer points, as on the slide, then removing Sk gives you interpolants with smaller norms than you would get by removing S. And there's some slack in this. There are constants C both in the comparison of the norms and in the number of elements. So it means that these SKs are sort of optimal. And moreover, this enumeration can be computed in polynomial time. And the algorithm for that is some recursive thing in which at each stage you throw in a few more points based on an application of the refined finiteness theorem. But I think if I explain it, I'm going to fall behind. Let me just ask how long I've been talking.
21 minutes.
Wonderful.
22 minutes.
Okay, great, thanks. Okay, so let's talk about CM alpha now. Instead of just CM, we have CM with Holder alpha. And the answer is it's the same story. Okay, so I won't state the theorems, but it's the same story. All right, so now let's talk about Sobel of spaces. So this is joint work with Aryeh Israel and Kevin Luley. And so remember that the spaces are as follows. We could have either an inhomogeneous Sobolev space WMP, the space of all functions which together with their derivatives up to order m belong to LP, or we could be working in the homogeneous space of the homogeneous Sobolev space LMP with the semi-norm that involves only the LP norm of the highest order derivatives, and therefore, for example, all polynomials of degree less than m have semi-norm 0. So I'll speak about the norm in X, even though, of course, it's a semi-norm. Now, in all of these problems, we're given the values of f at individual points, and we're asked to interpolate. So functions in our space had better be continuous. Well, according to the Sobolev theorem, that happens if p is greater than n over m. N is the dimension of Rn, and m is the number of derivatives that are supposed to be in LP. So if p is greater than n over m, at least our functions in X are continuous, so the problem makes sense. But in fact, we only know how to prove theorems when p is greater than n, which has advantages that I won't describe here, but in particular tells you that functions in our space X actually have m-1 continuous derivatives, just immediately from the Sobolev theorem. Okay, that's for finite sets. Now for any set, finite, infinite, measurable, I don't care what, X of E denotes the space of all restrictions to E of functions in the Sobolev space X. And the norm in X of E, or the semi-norm, is simply the inf of the norm in X of all possible extensions. So given a function little f defined only on E, how small can you take the Sobolev norm of a function on all of Rn that agrees with little f? Of course, if E is finite, X of E consists of all functions on E, but our problem is then to understand something about the semi-norm. And if E is infinite, then it's not even clear what the space X of E is. Okay, and again, recall the convention that constants that involve the letter C depend only on the choice of the space X. And so because we're talking about Sobolev spaces here, that means that constants denoted C depend only on little m, little n, and p. Okay, so the first theorem is that there are linear extension operators. So for any set, I don't care whether it's finite, infinite, measurable, never mind, for any set E, there exists a linear map from x of E to x such that for any little f in x of E, first of all, Tf agrees with f on E, so Tf is an extension of f from E to the whole of Rn, and Tf belongs to x. And furthermore, T has bounded norm. T has bounded norm as an operator from x of E to x. So you can produce an essentially optimal extension depending linearly on the function to be extended. Okay, now suppose that E is finite. Let's say, as usual, that there are capital N points. Okay, then a linear extension operator can be computed efficiently, but I have no time to discuss that, and so you will be spared the details. But as a result, the analog of the algorithms that I gave for, that I stated for CM apply also in Sobel of spaces. Namely, you can compute an essentially optimal extension using O of n log n one-time work, O of log n query work, and O of n memory cells of RAM. In addition to that, we can find the order of magnitude of the norm because there's a formula for it. So given a subset E, in place of those little subsets S1 through SL in the CM version of things, there are linear functionals Xc1 to Xcl mapping the space X of E, in other words, all functions on E into R, with the following properties. First of all, there are not so many of them. The number of these linear functionals is at most big O of n. Secondly, if we define a triple norm by taking the little LP norm of what you get by applying each of those linear functionals to a given f, then the triple norm is comparable to the norm of little f in X of E. And furthermore, the X's have a sparse structure for which I have no time to give details. But the result of the sparse structure is that if you give me a function, I can compute all the X's and therefore the triple norm of E using O of n in computer operations, linear time, once the X's are known. So, well, if you can compute the X's, life is good. And you can compute the X's. They can be computed in n log n operations with at most Cn storage. Okay, so that's the story for Sobel of spaces. All right, so far I've only been talking about finite sets, and I've been interested in algorithms, and the theorems have arisen in large part as motivations and beginning for the algorithms. Let me now talk about Cm of E when E is infinite. So this is actually the classical problem posed by Hassler-Whitney in 1934. The Whitney extension theorem was a first step in dealing with this. So suppose we're given some now infinite set E in Rn. We're given a function little f, real valued, let's say, on E. We want to decide whether it can be extended at all to a function in Cm, never mind the norm. Can it be extended at all to a function in Cm? How can we decide? Okay, now to solve Whitney's problem, we're going to generalize it, and then we'll solve the generalized problem. And it turns out that unless you generalize it, I have no idea how to solve Whitney's problem. We'll see why. Okay, so let's introduce notation. Well, first there's the previous notation. Jx of f, the jet at x of f, is the nth degree Taylor polynomial of f at x. And script p, remember, is the vector space of all possible such polynomials. Okay, now there's a natural multiplication of jets in which you multiply two polynomials. That may be a polynomial whose degree is twice as big as it should be, and so you take the jet at x of that product. The basic property of this product, dot sub x, as on the slide, the basic property of that is that if you multiply two smooth functions together and take their jet, and take the jet of the product, that is the product of their jets with respect to this funny operation. And so that means, all right, so this is simply, all right, that means that Rx, the ring of M jets, is simply the vector space script P with this operation. Note that as x varies, this ring varies. Of course, all those rings are trivially isomorphic, but they're not identical. So let me be pedantic and keep the dependence on x. So that's R sub x. Okay, so armed with that notation, let me give the generalization of Whitney's 1934 problem. So given a compact set in E, without loss of generality, E is compact because this is a local problem, and if E is not closed, you easily pass to the closure. So given a compact set E, suppose that for each point of x, you are given a translate of an ideal in the ring Rx. So here f of x is in Rx, and I of x is an ideal in Rx, and so this is a coset. This reminds me of the algebra that I studied in order to pass my qualifying exams once upon a time. Okay, problem. Given all that, decide whether there exists a CM function whose jet belongs to the given coset for each x in E. That's the generalization of Whitney's problem. We'll see why it's a generalization of Whitney's problem. We'll see why you need to generalize, and we'll see what the solution is. But first, a little terminology. So let's look at this collection of h of x for x in E, and let's call that script h. That's a bundle, with apologies to geometers. That's a bundle. And h of x is the fiber of script h at x. Notice that I made absolutely no assumptions about how h of x depends on x. The dimension of h of x need not be a measurable function of x. Okay. A function is called a section of a bundle if the jet of the function belongs to the fiber for every x in E. So our generalized Whitney problem asks, how can we decide whether a given bundle has a section? So that's simply the preceding problem with a little jargon. Okay, let's look at an example. Suppose that little phi maps the set E into the reals, where E is a compact subset of Rn. Now for each x in E, let's take f of x, that's supposed to be a polynomial. Let's take it to be the constant polynomial whose value at all points is just phi of x. So f of x is a constant polynomial on Rn, and I of x is the ideal in R of x consisting of all polynomials that vanish at x. That's an ideal. Okay, then it's a trivial remark that that a given function f in Cm is a section of that bundle if and only if it agrees with the function little phi on E. And therefore, our problem generalizes Whitney's problem because the function little phi extends to a Cm function on Rn if and only if some particular bundle that you can easily write down has a section. Okay, so we want to know whether a given bundle has a section. Okay, so we have to solve the generalized Whitney problem. Well, before we do, I'd like to make one small change in the definitions. And so it's convenient to make the following strange-looking change in the definition of a bundle. So the convention is that we will allow the empty set as a fiber at any given point. And so a bundle now is defined as a collection of h of x's where for each x in E, either h of x is a translate of an ideal as before, or h of x is the empty set. That seems rather strange. You'll see why in a minute. You'll see why it's strange immediately. You'll see why we do it in a minute. Okay, of course, if H has any empty fibers, then it has no sections. Guess what? Okay. Now, following the early work of Glaser and the more recent work of Bierstone, Millman, and Pawlutsky, we're going to define an operation on bundles. It's called Glaser Refinement. So given a bundle H with fibers H of x, we're going to produce its Glaser refinement, which is a new bundle H tilde, whose fibers are H tilde of x, x in E. H tilde might have some empty fibers, which is why we changed the definition before. Even if H doesn't, H tilde might. Okay, so I don't have time to tell you what the Glaser refinement is. It's not so complicated, but I don't have time. I'd like to tell you the good properties of the Glaser refinement. First of all, H tilde is a subbundle of H. That is, for each point x, the fiber H tilde of x is contained in the corresponding fiber H of x. So the fibers are getting smaller. that in principle means that it's harder to be a section of H tilde than it is to be a section of H. But in fact, every section of H is already a section of H tilde. And so somehow we're peeling away irrelevant junk from the fibers of H. Finally, H tilde can be computed from H by doing some linear algebra in fixed dimension and passing to a limit. So this thing is computable. Okay. So therefore, if we want to know whether a given bundle has a section, we might as well replace it we might as well replace the bundle by its Glaser refinement. We have made progress by peeling away some irrelevant junk. Okay, well, if that made us happy, we can get even happier by iterating. So given H, we can define a sequence of successive Glaser refinements. Let's say H0 is the bundle we start with. H1 is the Glaser refinement of H0. H2 is the Glaser refinement of H1, and so on. And so we can keep going. And as we do this, we peel away more and more irrelevant junk, and so we get happier and happier. There's the danger that we get happier and happier forever and never make any further progress and never solve the problem. But in fact, that's not the case. Well, there are the properties of all the HL. You can compute them because you know how to once you know how to compute a bundle, you can compute its Glaser refinement. And again, we may have lost, the fibers may have gotten smaller, but the sections are always the same. But now the process stabilizes. There's some capital L star that is something like twice the dimension of the space of all Taylor polynomials. And once you get to that stage, the process stabilizes. And so you have discarded all the irrelevant junk that you can possibly discard by this method. And so that's the stable Glaser refinement. And in principle, you can compute it. And once you've done that, then you can read off the solution of our original generalized Whitney problem, which is that our bundle has a section if and only if its stable Glaser refinement has no empty fibers. Of course, if the stable Glaser refinement has any empty fibers, there's no way H can have a section. But conversely, that's the only thing that can go wrong. And so that decides the generalized Whitney problem and therefore the Whitney problem. We had to generalize the Whitney problem because the higher Glaser refinements of a given bundle H no longer arise directly from any particular Whitney extension problem, but they're merely bundles. Who knows which bundles? Okay, so that's the solution of Whitney's 1934 extension problem. Okay, let me give a quick application on the border of analysis and real algebraic geometry. I've always had, I mean, for many years, I've had the feeling that the connections between this subject and real algebraic geometry are a lot closer than is apparent right now. And this is a bit of evidence for that. So there is a problem that arose on the border between analysis and real algebraic geometry that these methods solve. How much time have I used so far?
38 minutes.
Great. Okay. So I'd like to start with an example due to Mel Hochster. This has to do with functions of three variables. So let's say capital F is a continuous function of three variables. There on the slide is an equation for three unknown functions, little f, little g, and little h. Now we want to solve this equation with capital F given. We want to solve for these three unknowns, little f, little g, and little h. And we would like to know whether there is a continuous solution. Okay, there are obviously lots of solutions because it's one equation in three unknowns, but can we pick the solution to depend continuously on x, y, and z? Okay, now let's suppose first that capital F is a C infinity function, but we still are interested in whether we can solve this problem with continuous little f, g, and h. Well, then it's an exercise to show that for C infinity capital F, there's a continuous solution if and only if the conditions in the box there are satisfied. That's a little strange. In particular, note that although we want merely continuous solutions, our conditions on capital F involve derivatives up to third order. Let's go back to the box for a minute. There. Notice we're differentiating capital F up to 3 times. Okay, so that's what happens if if capital F is C infinity. How about the original question when capital F is merely continuous? How can you tell whether there's a continuous solution little f, g, and h? How can you tell? I'm not going to tell you, but it can be done. Okay, but in fact, in the full problem, we're given functions. I mean, that was an example. The full problem is this. Given functions, let's say q1 through qn and capital F in Cm of Rn, decide whether we can solve the equation, the one equation, that the linear combination of the q's with coefficients little f1 through little fn, that linear combination is equal to the given capital F with Cm, not merely continuous, but Cm solutions. And, well, this problem can be solved. There is a way of taking problems of that form and Glaser refining them. And if you successively Glaser refine in a finite number of steps, you can decide whether a solution exists. Let's see. So, okay, in the C0 case, this is written up in a paper by János Kollár and me. Kollár sent me an email one day telling me about the problem and asking me, do I know anything about it? I said, hell no. But then it occurred to me it was actually related to stuff I'd thought about for a long time. I sent back a reply, hell yes. And we have a joint paper containing two solutions of the C0 problem, one consisting of analysis and the other consisting of algebraic geometry that I wish I understood. Okay, the CM case is joint work with Kevin Lully, and it's based on ideas in the solution of the 1934 Whitney problem. Okay, now in a further development, okay, we could go back to the C infinity version, and the generalization of the C infinity version is what's on the slide. Given capital Q1 through capital Qn, and given little m to tell us which differentiability class we're working in, there are linear partial differential operators with semi-algebraic coefficients with the following property. Given a C infinity function capital F, the relevant linear equation in the unknowns little f1 through little fn can be solved with a Cm solution if and only if those linear operators annihilate capital F. So an example of one of these linear operators might be, let's say, a third derivative of capital F evaluated at the origin and 0 elsewhere. So this contains the discussion of the example. Okay, and in principle, these L's can be calculated, and from those L's one can actually calculate the ideal of all polynomials capital F for which there is a Cm solution. I'd be interested to know whether, if there's a solution in Cm, the little f's can be taken to be semi-algebraic. That seems to be a hard problem. Okay, let me end the lecture with two results on a variant of the preceding discussion. So far, we've always had a function defined on some finite or infinite set of points, and we're interested in functions capital F that are as smooth as possible and that agree perfectly with the data. Now, every experimentalist trying to fit some function or other to data deals with the fact that the function is not expected to fit the data perfectly. And so we're in the business of trying to fit functions, smooth functions, approximately to data. In connection with that, I'd now like to discuss Cm and Lipschitz selection problems. The Cm work is joint work with Aryeh Israel and Kevin Lully, and the Lipschitz selection problem is recent joint work with Pavel Schwarzman. Okay, so here's the problem. We're given a finite subset of Rn, but we're not given a function value anymore for each point of E. Instead, for each point of E, we're given a convex subset, k of x, in Rd. And the idea is that our functions are going to be Rd valued, and they will approximately agree with the data if they lie in those convex subsets. So so given little m greater than or equal to 1, a Cm selection is a function, capital F, in Cm of Rn, taking values in Rd, such that the function value at x belongs to the prescribed convex set k of x for all x in E. And the question I'd like to pose is, how small can we take the Cm norm of such a thing, such a Cm selection? And the result is a finiteness theorem, which is the analog of the original Brudny-Schwarzman finiteness theorem of several decades ago. And so this subject is just beginning. So for large enough constants, k sharp and c, determined by the function space, namely little m, little n, and d, for large enough such constants, the following holds. Suppose you're given any selection problem. So we're given, suppose we're given any little subproblem. So we're given any subset capital S contained in E with at most k-sharp points. And suppose that for any such small subproblem, there is a selection Fs depending on the particular subproblem with Cm norm, let's say, less than or equal to 1, that hits the targets, that is, capital F S of x belongs to k of x, but only for x in S. Suppose that that's true. Then there's a solution to the whole problem. There is a function capital F that takes values in k of x for all x in the set E, no matter how many billion points it has, and the norm of that capital F is less than or equal to c. So that's the finiteness theorem for that. It's the analog of the original Brudny-Schwarzman theorem. And so this subject is just beginning, whereas the subject of interpolation with perfect agreement is in much better shape, as I hope I've convinced you. Okay. So the finiteness theorem was proven maybe a year ago, but it also, I want to give a lot of credit to Brudny and Schwarzman for many of the many of the ideas that underlie it, and there are those ideas on the slide. Okay, and here are some special cases which Pavel Schwarzman had proven before the. Oh, I'm sorry. Yes, this is just for Lipschitz selection. Okay. All right. Let me now go to Lipschitz selection. So if our notion of smoothness is merely Lipschitz continuity, we needn't be restricted to Rn. We can work in a general metric space. General metric spaces are, in fact, very interesting. So suppose we're given a metric space, and for each point of the general metric space, we're given, let's say, a compact convex set K contained in Rd. We want a Lipschitz map from the metric space into Rd that takes values in the convex set K of x for each x in the metric space. And the theorem, joint work with Pavel, very recent, being written up now, is this. Suppose that for every subset with at most 2 to the d points, so in fact 2 to the d is the best number, that's the analog of k sharp, but for this theorem we know exactly what it is. So suppose that for every subset with at most 2 to the d points, there is a function mapping just that subset into Rd with Lipschitz constant less than or equal to 1, and that whose value at each point of the small subset S belongs to the target k of x. Then, under that assumption, there is a function capital F from the whole metric space into Rd with a Lipschitz constant that depends only, in fact, only on d. That's the only parameter in the problem, such that f of x belongs to k of x for all x in the metric space. So you can solve Lipschitz extension problems provided you can solve all little subproblems. Okay, well, once we know how to do that, the subject is started, but we don't at all know how to find efficient algorithms to solve any reasonably general CM or Lipschitz selection problems. So for example, here's a selection problem that I would love to solve, and I don't know a good solution. So suppose that we're looking for an unknown function on the line. So our functions are supposed to be defined on the x-axis. The curve in question, the curve here is a hypothetical selection capital F. And the set E is just a finite number of points on the line. I've marked them with little hash marks on the x-axis. And above each hash mark is a little window, let's say a center point and an error bar. And let's say we've made an experiment and we sincerely believe that the true value of capital F, whatever it is at each point, lies inside the error bar. We want to draw the graph of some nice function that sits inside, that passes through all the windows as in the picture. How small can we take the C2 norm of such a thing? That's a very elementary question, and we don't know a good algorithm for that. I can tell you an algorithm that works in polynomial time as a consequence of the work with Aryeh and Kevin, but I don't even know which power of the number of points is required. It's clearly too big. I would conjecture that there is a solution in O of n log n time, just as for the previous incarnations of the interpolation problem, but that's just a wish, and so in fact I don't know. So very, very simple questions about fitting smooth data, smooth functions to data are still unknown, and well, that's not a complete survey of the state of the subject, but I think it's enough to give you an idea of the nature of the problems. I hope you found it interesting. Well, all right, abandoning the slides and just returning a bit to virtual real life, I'd just like to say again what a great pleasure it is to take part in something in honor of Eli. Eli is a wonderful mathematician and a wonderful person, and he's had a tremendous influence on my own life and on many, many other lives, and just all my gratitude and best wishes to Eli. Thanks.